interactive online training on piping and instrumentation diagram. Module 2. Preliminary Engineering Drawings. Following topics to be discussed in this module. 1. Block flow diagram, PFD. 2. Process flow diagram, PFD. 3. Piping and instrumentation diagram, P&Id. 4. Heat material balance. 5. Quiz. A block flow diagram or a block schematic diagram is a simplified representation of a process flow diagram. Unit operations or processes may be represented by rectangles, or by a cut block of a piece of equipment. Each block shows an activity, such as storage or treatment, performed on the primary streams only. Blocks are connected by straight lines and flow arrows, and represent a mixture of liquids, gases, or solids moving through the facility. Similar to PFDs, a block flow diagram does not show bypasses, secondary lines, or line numbers. In order to create a well-versed PFD, the following steps are recommended. A. Arrange all major pieces of equipment in unit operations. B. When multiple pieces of equipment exist in parallel, they may be shown as a single item. C. The equipment need not have numbers, but should show the process or operation that it conducts. D. Connect the pieces of equipment with straight primary lines and show flow arrows. E. Flow directions should always go left to right. If they cross, the horizontal line takes precedence over the vertical line. F. Light stream, gases, toward top with heavy stream, liquids, and solids, toward bottom. G. Only the most critical process information needs to be supplied. H. This could be the name of the product or function. After implementing the above procedural guidelines, a PFD is generated as below. Process flow diagrams are used in chemical and process engineering. These diagrams show the flow of chemicals and the equipment involved in the process. Generally, a PFD shows only the major equipment and does not show details. It shows the relationship between major equipment and components of a plant facility in the system. PFD also tabulates process design values for the components in different operating modes, typical minimum, normal, and maximum. PFD does not show minor equipment and items such as piping materials of construction, piping sizes, piping components, piping systems, piping ratings and designations. A PFD should include A. Process piping. B. Major equipment symbols, names, and identification numbers. C. Control, valves, and valves that affect operation of the system. D. Interconnection with other systems. E. Major bypass and recirculation lines. F. System ratings and operational values as minimum, normal and maximum flow, temperature and pressure. G. Composition of fluids. PFDs should not include A. Pipe class. B. Pipeline numbers. C. Minor bypass lines. D. Isolation and shut-off valves. E. Maintenance vents and drains. F. Relief and safety valve. G. Code class information. H. Seismic class information. The PFD displays the relationship between major equipment of a plant facility and does not show details such as minor equipment items, piping materials of construction, and pipe sizes. Note that the process flow is easily distinguishable, contains no instrumentation or controls. A piping and instrumentation diagram is a schematic illustration of functional relationship of piping, instrumentation, and system equipment components. The P&Ids are used to operate the process system. Following slides show various views of a typical P&ID example, since the resolution of the drawings is not high enough to display clearly on one screenshot. The next slide is the complete display of the previous P&ID views. A P&ID should include A. Instrumentation and designations. B. Mechanical equipment with names and numbers. C. All valves and their identifications. D. Process piping, sizes and identification. E. Miscellaneous, vents, drains, special fittings, sampling lines, reducers, expanders and swages. F. Permanent startup and flush lines. G. Flow directions. H. Interconnections references. I. Control inputs and outputs, interlocks. J. Interfaces for class changes. K. Seismic category. L. Quality level. Annunciation inputs and computer control system input. Vendor and contractor interfaces. P. Identification of components and subsystems delivered by others. Q. Intended physical sequence of the equipment. R. Equipment rating or capacity. A P&ID should not include A. Instrument root valves. B. Control relays. C. Manual switches. D. Primary instrument tubing and valves. E. Pressure, temperature, and flow data. F. Elbow, Gs and similar standard fittings. G. Extensive explanatory notes. In order to generate a P&ID, familiarity with all the symbology, terminology, and abbreviations is of the essence. P&ID symbology has been discussed in detail in the modules to follow. Throughout this course, ISAS 5.1 standard has been referenced for P&ID symbology. Before proceeding to next module, the concept of equal material balance must be examined in order to understand its significance along with PFD. Heat and material balance is an application of conservation of material to the analysis of physical systems. By accounting for material entering and leaving a system, material flows can be identified which might have been unknown or difficult to measure without this technique. The exact conservation law used in the analysis of the system depends on the context of the problem that is matter can neither be created nor be destroyed. Therefore, material balances are widely used in engineering and environmental analyses. Material balance is a fundamental document generated by process design engineers while designing a process plant. Sometimes heat and material balance is not a separate document, but appears alongside the process flow diagram. A typical heat and material balance flow block diagram is shown below. A heat and material balance sheet represents every process stream on the corresponding PFD in terms of the process conditions. Normally, a heat and material balance sheet reports following data for a process stream. A. Normal operating temperature and pressure. B. Normal volumetric or material flow rate. C. Density at normal operating temperature and pressure. D. Viscosity for each phase in the stream. E. Gas vapor fraction. F. Specific heat ratio Cp and Cv and compressibility factor for gases. G. Molecular weight. H. Enthalpy flow kilojoules per hour. Heat and material balance calculations for a process are performed by applying the material balance equation and the energy balance equation to each equipment. The system has a unique solution when number of unknown variables is equal to number of equations. Therefore, some variables are fixed to solve the system. If inlet streams are fully known and defined, then the system is solved to know the outlet streams. If the required properties of outlet streams are fixed, then system can be solved to know what should be the inlet to get the required outlet streams. Identify whether the statements below are true or false. A block flow diagram does not show bypasses, secondary lines, or line numbers. True. A PFD shows piping sizes and piping ratings. False. A PFD should include control valves and valves that affect operation of the system. True. PFD should include relief and safety valves. False. A P&Id should not include all valves and their identifications. False. A P&Id should not include control relays and manual switches. True. Heat and material balance sheet reports normal volumetric or material flow rate, viscosity for each phase in the stream, and molecular weight. True. And this is the end of Module 2. In the next module, symbology on piping and valves shall be explained.